Alright guys, I'm going to show you something really awesome here about this problem. Okay? So we're looking at the interval 0 to 1. Watch this. Here's 0, here's 1. I'm going to take any partition. I don't care what it is. Chop it up however you want. Okay? Now, when I look at UPF minus LPF, right? Let's remember how we would calculate that. The UPF is the sum of the delta xi's times the capital Mi's, and the LPF is the sum of the delta xi's times the little mi's. So I can view this as, you know, let's just think of it as two parts here. There's the M1 delta x1 plus M2 delta x2, and these are big M's, up to Mn delta xn, and then minus little m1 times delta x1 plus little m2 times delta x2 plus dot 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 plus little mn times delta xn, right? And what you'll notice though is that there is a lot of similarity between the terms. Let me draw the graph one more time. Actually, I can draw it up here. I guess sine of 0 is 0, and it kind of goes up something like that, right? So the big M1 is the maximum value of the function on the first interval. That would be this value right here. But that is also the same as little m2, because the minimum value of the function on the second subinterval is right there at the left-hand endpoint. So big M1 is the same as little m2. Doesn't even matter what the partition is. That's true in this case. Similarly, big M2, which is at the right-hand end of the second subinterval, agrees with little m3. So big M2 agrees with little m3. You see, these things cancel. It's because the function is monotone, right? It's actually monotone increasing, so that the highest value of one subinterval is the same as the smallest value on the next subinterval. So when you subtract them, which is what you want to do for this theorem, when you subtract them, they cancel. The only thing that survives the calculation is the very biggest term at the far end, at the far right, minus the very first term right here, which looks like that. Okay, and big Mn, well, that's just sine of 1. And little m1 actually is just this point right here is 0. So this term is also 0. So we just get sine of 1 times delta xn. Right? And I want this to be less than epsilon. So remember the way that this proof would begin, so we're going to prove that the function is Riemann integrable by using this theorem. The first line of the proof is let epsilon greater than 0 be given. I didn't write that down yet, did I? So the proof, this is by the way, this would be considered your scratch. Remember how you often have to do scratch work? You start with an epsilon and you work backwards and you find what? N naught or a delta, and now we're finding a partition, right? So this is really the scratch work. So the actual proof then, I guess I can erase this top part here. The actual proof is simply going to start off with let epsilon greater than 0 be given. What you could do if you wanted at this point is you could say something like this. Choose any partition P of the interval 0, 1 such that delta xn, the width of the final subinterval, is less than epsilon over the sine of 1. Now that's not being very explicit. So I'll help. If you don't like that, if that seems too vague to you and you want to have a more precise, actual specific partition, I'm going to show you in a second how to do that. Okay. But let's just say for now, I'm just going to basically, I'm going to choose my partition so that this last chop right here, it makes a small enough subinterval so that by the time I multiply by sine of 1, it's less than epsilon. Okay.
Dr.
So, yeah.
I have a quick question
Go
before we
ahead.
move on.
Uh-huh.
I don't see how our M1 delta x1 and our M2 delta x2 cancel unless we're assuming that delta x1 and delta x2
you're
are
right.
the
You're
same.
right. You're right. You're right. You're right. You're right. You are absolutely right. Because I forgot to make all my subintervals equal width. You could, of course, just replace, like you could compare the two deltas and replace with the larger one, and so that they would be the same, and then cancel them. But you're absolutely right. So let me just do my. That's the next thing I was going to talk about anyway. So let me just be more specific here. So more specifically, choose P sub n. If you've watched my video, you know what this is about. Where n is large enough. I'll explain this in a second. So that 1 over n, 1 over n is less than epsilon over the sine of 1. So remember what P sub n is, for those of you who haven't had a chance to look at the video yet, it's basically just chopping this subinterval up into n equal pieces, and the delta xi's are therefore all the same. They are all the same width, which is you take the full interval b minus a, and you divide it into n equal pieces. Okay? Now this is not every possible partition that you could make, but this gives you actually an infinite family, a countably infinite family of partitions that are indexed by n. Right? And the bigger n is, the smaller each of these subintervals is going to be. The idea behind that is, if you do that, then all of these delta xi's are actually the same. So then when you subtract, they really do cancel. Okay, so I think my scratch work is still going to be fine. I just had to be more specific here. So let's just say, choose, let's just cross that off. There we go. Choose P sub n, where n is large enough so that 1 over n, which is delta xi, for each I, will be less than epsilon over n. So, retracing the scratch work gives u of pnf minus L of pnf less than epsilon. Okay, so that's a good strategy to use there. Does that make sense? All we're being asked to show is that the function is Riemann integrable. So I only need this theorem. And because it's a monotone function, basically on Monday I'm going to prove the theorem that says every monotone function is Riemann integrable on whatever the domain is, on whatever that interval is. And you sort of see the proof already in this example. It's not going to be really much different than that when I present it in class, so I hope it'll seem really easy to you. Does that make sense, guys? Okay. And the other thing we're going to learn is that every continuous function is Riemann integrable on any domain on which it's continuous. So continuous functions, monotone functions, they're all going to be good. There are lots of good examples of Riemann integrable functions out there. Lots of functions are Riemann. So for example, this function here, right, that's Riemann integrable because it's monotone increasing. Even though it's got jumps in it, it's not a problem. Okay? And a continuous function, right? That's Riemann integrable on any domain, right? Because I've drawn it without picking up my pencil. So it's a Riemann integrable function as well. Lots of things are Riemann integrable. So I guess that begs the question, can somebody remind me what would be an example of a function that is not Riemann integrable?
You just want an example?
Yep, I want an example.
Okay, f of x is equal to
x's in the rationals,
Okay?
and -1 when it's not.
Love it. Absolutely right. Okay? Perfect, because that leads me right into the next question we're going to do. So keep that on the board. How did he know that example? Because he came to class or something. Is it in the homework?
Well, it helps with
It does help with the homework. Okay. I was going to say, we did this basically in class. I gave you this example. The idea is that every upper, well, and we need some interval here, but actually any interval will work. Every upper sum is just b minus a, and every lower sum is just negative of b minus a, and those aren't the same. So your infimum of all of your upper sums is just b minus a, because every one of those individual upper sums is b minus a. And the supremum of all of your lower sums is just negative of b minus a, because every one of those lower sums is just negative of b minus a. All of those things can be pretty quickly shown. So with that in mind, I want to do problem 4 on the handout here. Okay, so I'm not going in order on these problems, but it says, give an example of two functions, f and g. I want f to be not Riemann integrable. I want g to be not Riemann integrable. But I want f times g to be Riemann integrable. So I'm going to give you 30 seconds to think about it. And then I'm going to see if anybody's got an idea. By the way, you'll notice this function, it's not continuous, and it's not monotone. Both of those two quick ways that a function can be Riemann integrable fails. Has that been 30 seconds? Jason, what do you think?
Can you just let g be the same function?
Okay, if you let g be the same function, so we already know that f and g would then not be Riemann integrable. Okay, so this is also g. Okay, that's good. So then what is f times g? So that's f of x times g of x.
It's 1 everywhere.
It's always 1, right? So is the constant function 1 Riemann integrable?
Yeah.
Why is that?
It's monotone and continuous.
Monotone, can you give me a reason that doesn't rely on a theorem I haven't really stated yet? Because you've actually got a better reason you can give them.
Well, big capital MI and little mi are the same.
They're all the same.
Yeah.
Every upper and lower sum is the same. It's really that first homework problem on that assignment that you get. Oh, not the first homework. The first homework problem in section 6.1 that you guys did on that assignment that I just passed back, which just says if you have any constant function, then it's Riemann integrable. So, yeah. So this is by exercise 6.1, number 1. Or just because it's clear. Okay. We'll have about 5 reasons why that's Riemann integrable by the time I do these theorems this week. So, okay, so that looks good to me. All right, let's move on. Move backwards, I should say, and do problem number 3 on the sheet. I think I want to do that one next. This one's a little more. This one will make us think a little bit more. What this says is, suppose that you have a continuous function from a, b to the real numbers. So continuous. And it's always at least 0. So it's non-negative outputs. But there exists, we're going to assume that there exists some point C in the open interval AB such that f of C is equal to 1. Now here's what we want to do. Oh, so first things first. You're going to have to take my word for it that every continuous function is Riemann integrable. I've already said that once today. We haven't actually officially stated that yet, but when you see what I'm about to write down, you'll understand why I have to assume that. Because what I'm going to ask you to prove in part A, actually I'm only going to do part A anyway, so to say prove. What I'm going to ask you to prove here is that this Riemann integral of f on that interval is strictly positive. So if I'm writing this symbol down on paper, it means I'm already assuming the function is Riemann integrable. Remember, this symbol doesn't make sense unless my function is Riemann integrable. So please be careful. If you don't have a function that you know is Riemann integrable already, you shouldn't be writing this symbol down on your paper yet. Okay? Because this symbol was introduced as a notation. Once we know that a function is Riemann integrable, here's the notation for the value of it. And we want to show that it's positive. So I think intuitively this makes pretty good sense. So here's my closed interval from A to B. And my function has to be above that axis because it's always non-negative. But there's some point somewhere, I'll call it C, where the graph has to come up and touch the value of 1. And because it's continuous, it can't just jump up to 1. Right? It has to actually, I mean, it might be hugging 0 for a while, but eventually it's going to have to spend a little bit of space here to hop up and hit 1 and come back down. It can't just jump up there in no distance. There's got to be some distance there. And therefore, you can see that the area under the graph has now become positive because it's never negative, right? But it has to be more than 0 at some point. So this is what we want to actually prove, that this is positive, and I'm assuming already that this integral makes sense. So this is not an issue of theorem 6.2, right? Theorem 6.2 is if I'm testing for Riemann integrability. That's not what I'm doing right now. I already have a Riemann integrable function, and I want to evaluate, or at least say something about the value of it. Okay, so what do you suppose we're going to do? We really don't have any theorems yet for how to evaluate integrals. And later on, we're going to end the course with the fundamental theorem of calculus, which is going to be the grand finale, exciting theorem, right? That'll help us to evaluate integrals. We're going to have theorems about how, well, if we know how to evaluate simple integrals, then we can add them and subtract them and multiply by scalar, all of that. So we'll have basic properties of these integrals. We don't have that so far. Okay. Other than that, we really just have the definition. So the definition that we know is that the definition of this integral is that it actually equals two common values, right? It equals the upper and lower Riemann integral. So there's that one and that one. Right? And the upper Riemann integral, if you remember, is the infimum of all of the upper sums. And the lower Riemann integral is the supremum of all of the lower sums. And we are given that these are the same. So I'm going to give you a hint that we need to compute one of these two, or we need to make an estimate on one of these two. My question to you is going to be, and this is the crucial point, which of the two should I work with? Should I be thinking in terms of lower sums or upper sums in order to make my case here? A little more specific here. This is such that P is a partition, and this is P is a partition. Let me throw this at you. Let's suppose I choose a partition of AB. any partition, I don't know, whatever. I choose a partition of AB, and I calculate the upper sum for that partition, and I get 0.7 for that particular upper sum. Is that going to help me say that this is greater than 0? No, it's not, because, all right, sure, I got a 0.7 for one of my partitions, I got a 0.7 here, but I have to take the infimum over all upper sums, one of which gave me a value of 0.7, but I have all sorts of other upper sums that might be less than that. Okay? All right, start over. Say I take the same partition. Let's say I calculate the lower sum for that partition, and let's say I get 0.7. Does that help me?
Yeah. Has to at least be that.
Ah, if I get 0.7 for one of my lower sums, then the supremum, see, supremum is the least upper bound. The least upper bound would then have to be at least 0.7, which would be greater than 0, you see. You see the difference? So which one would we rather work with? The first one or the second one?
Second one.
That's right. Okay. So, because see, the value of this is if I just simply find one partition that gives me a positive lower sum, then I'm done. I've got what I want to prove. So let's come back to the picture again. Take off all these marks. Can you think of how you would want to construct a partition, just looking at this graph? Would there be a natural way to try to construct, at this point we just want one partition that gives us a positive lower sum. Would there be a natural way to try to create that partition? Remember, the lower sum is, you know, the little mi times delta xi.
I think so. Can't we use...
Does it matter what I do over here?
No.
No, I'm going to get 0 for all that, right? So what do I want to make sure happens as I'm chopping up my interval?
That you have something where the lowest value is greater than 0. So could we use intermediate value here? Because we have a C where we know we have a positive value.
And the intermediate value theorem says you got to pick a value of k between f of c and f of some. Well, actually, we've called this f of a and f of b, right?
Mm-hmm.
So what value of k would you use?
Just something that's between C and, or sorry, we want something that's between f of C and f of 0, or f of something that equals 0. So we have
if
a
that
value,
even happens.
yes, so we have a value between 1 and something that's greater than or equal to 0.
Mm-hmm.
So it means we have a positive value there, and so now we have an interval where we can have positive value and positive value, so it has to be positive.
Right. Okay, I like your thinking. Basically, that will work. But let me just bring it back to something even more basic than that at this point. What we really want to do, guys, is create a chop there and there, right? We want to create a chop so that throughout that one subinterval, this is just some delta xi subinterval among the whole partition, the little mi for that piece is not 0, right? We want it to be strictly positive. And so Nathan was suggesting a way of doing that by using the intermediate value theorem. I was going to say, you know, just choose k equal to 1/2 maybe, right? The only thing is, see, you don't know. What if your function actually stays up here the whole time and you don't actually get 0, or maybe it's not as low as 1/2 ever. So you'd have to iron out that detail. So I think there's actually an easier way to actually create this delta xi, this one little subinterval of the whole partition. And then the rest of, after that, I don't care what you do. I don't care what you do in the rest of the subinterval. It's just this one little piece. Okay. So instead of using the intermediate value theorem, which I think you could make that work, but I don't want to go make my head hurt today and try and figure out the details of it, we can actually just simply use the definition of continuity. We do need continuity here, right? That assumption is important, and I haven't used it yet. So the definition of continuity at C, I'm going to focus on the point C, is that for all epsilon greater than 0, there exists a delta, such that if the absolute difference x minus c is less than delta, then the absolute value f of x minus f of c is less than epsilon. That's true for all epsilon greater than 0. That's given. So can you think of an epsilon that we might want to use? Because we get to choose an epsilon here. This is not let epsilon greater than 0 be given, right? That's if we were proving continuity, we would let epsilon greater than 0 be given. We know continuity, so we get to pick an epsilon. An epsilon is going to create a window, a horizontal strip, right, that has 1 at the center of it. Got an epsilon in mind that we could work with? Pardon?
1.
Okay, let's try that. I don't think it's going to work, but we'll try it. Let epsilon equal 1. So that means my window is actually going from 2 to 0. Like that. Actually, this might work out okay. Let's see how it works. Okay, so we pick an epsilon. So since f is continuous at c, there exists a delta greater than 0, such that if the absolute difference x minus c is less than delta, then the absolute value of f of x minus f of c, which is 1, is less than 1. And in other words, this really means that f of x is between 0 and 2. Okay, so in other words, I'm going to rephrase this right here. X minus c being less than delta is just another way of saying that c is between, x is between c minus delta to c plus delta. So that's actually, so given this strip here, there now exists this domain in here, right, c minus delta to c plus delta, right, and if x is in there, then my function is positive, right? See, what I'm getting at here, guys, kind of is that what I want us to do is to make this one of my subintervals. See, I'm allowed to construct any partition I want. Right now, what we said is we just need to find one partition that has a lower sum that's positive. The problem with this epsilon is that even though the function does have to be positive, as soon as you take the infimum, remember the little mi is the infimum of all of the f of x values on that subinterval, the infimum of a bunch of positive numbers could actually be 0. Like, what's the infimum of 1 over n? It's like 1, 1/2, 1/3, 1/4. The infimum is 0. Now, if that happened, then my little mi would be 0, and I wouldn't be sure that my lower sum would be positive. So I'm just going to fix that if I could. I'm just going to come back here and change epsilon to 1/2. Because if I do that, then this becomes 1/2. And then this becomes f of x between 1/2 and 3/2. Now, I know that the infimum of a set of numbers that's between 1/2 and 3/2 is definitely greater than 0. Right. Okay. So I'm going to choose any partition P that includes c minus delta and c plus delta as points, I'm just going to say as adjacent points, meaning they're consecutive points of the partition. That's actually not totally necessary, but to make the proof easier and cleaner, that's a better thing to do. Okay. So let's just say xi is c minus delta and xi